Guys, welcome back to another episode of Site Visit. I'm Nick Schiffer. We're here at 45 White Oak. This is our spec project in Wellesley, Massachusetts. A lot has happened since last time. Today, I'm joined by Ben Bolger from H+O, our structural engineer on the project. Last time we had them on, we walked through the entire structure of a previous project. We want to do the same thing today. So we're going to walk from top to bottom, but start with his reaction from the street. Ben, what's up, man?
Hey, Nick, how you doing?
Good to see you.
Good to see you too.
So we spent a lot of time on Zoom.
Yes.
This is your first time out on site.
Absolutely. Yeah.
First reaction.
It's pretty impressive. It's a lot bigger from the street than I expected.
We keep convincing ourselves that once the facade is on, it will kind of nestle in.
Yeah.
Because right now it's baby blue, and it's a big structure, and there's a lot to it. Working with the guys at Cape Cod Panel, working through all those details. What was that process like? Early on for you guys, thinking about like, hey, this is going to be built off site? Was there any different considerations in the design?
Well, we had a lot more control over, the shop drawings, right? Each wall panel. Cape Cod Panel is fantastic, and this is a pretty heavy structure because you have the Peterson cover brick on the facade and on the roof.
Yeah.
So everything's a little more beefed up.
Sure.
Yeah, so it's pretty impressive. And also seeing these retaining walls in person, I mean, the grade difference from front to back.
We had some conversations about the retaining walls, and I kept dumbing them down, being like, they're not that big, they're not like, it's not that big a deal. And now looking at them, I agree with you, like it's holding back quite a bit.
Yes, exactly.
Especially now that you see this whole, essentially carport area where you can fit almost 4 cars wide before you enter the garage.
Yeah.
But so I'd love to just walk through the whole project, and you're here today for a couple of reasons. Number one, to be on site visit.
Yep.
Number two, to basically give us a maybe blessing on how we built things and check, some of the things that we've talked about, via text and via RFI.
Right.
But what's important to you as you walk a project like this? Like, what are you going to be looking for?
We generally like to go either top down or down up. So first floor framing, second floor framing, look at the roof, make sure everything generally matches our drawings.
Yep.
Look for our Simpson Hurricane clips.
Yep.
We have a lot of steel in this project. Take a look at that. Base plates, cap plates, make sure all the connections are pretty much there. Hangers, joist to beam. We have some joist penetrations and beam penetrations that we've talked about, so I'd like to just take a quick look at that as well.
Cool.
And just generally walk through, and sometimes, other questions arise that we can take care of.
Cool.
Today, right?
Yeah. So the bridge itself, there's a W18, I believe?
Yep.
That spans these 2 retaining walls and essentially holds this deck structure up, which is also waterproof. It's funneling all the water out to a scupper and getting the water out. From an architectural perspective, it's getting this additional covered parking area. For you, the consideration here, I know there was actually an early conversation about doing this as a land bridge.
Yes, right.
Which I forget the math on it, but it was like something to the tune of a 30,000 pound structure.
Precast concrete beams.
Yeah, and I was like 30,000 pounds, and it was like, well, the earth and this, and you have to drive a tractor over it to cut the grass, and I'm like, so we ended up with this wood structure. So what were some of the considerations back in that early design process? Well,
clearly it's a big span, right? And it's spanning in between the retaining walls.
Yeah.
So not only do we need to design the beam for the span, but you're bearing on the concrete foundation wall, so you need to have like a nice kind of base plate and little stub column. You can kind of see that detail there.
Yeah.
And also on top of that, you have this planter, right? So it's going to be retaining soil. It's going to be heavy when it's saturated, and also it's a deck. It's an open deck, so we need to design for any snow that may occur, snow drift against the house, all the typical dead loads, and we wanted to keep the beam pretty stiff, right, and as light as possible. So, if possible, allowed us to go a little bit deeper up into the planter, and that kept the beam lighter while keeping it high performance.
You say by going taller, you're keeping it lighter. Is that because otherwise you'd have to go fatter or thicker flange?
Thicker, heavier, wider, all of that.
Got it. So essentially, as you're getting taller, you're essentially adding rigidity to that beam, so it's going to deflect less and less.
With more depth, you get more stiffness.
Got it.
Yeah, as a rule of thumb.
Yeah.
Exactly.
Where you're getting a shorter beam, you'd have to really thicken that steel.
It needs to get heavier to be as stiff as a deeper beam.
Got it.
Yeah,
okay.
Exactly.
Let's go inside.
Yeah.
A lot going on here. We have the insulators actually ahead of a lot of the mechanicals, because the building inspector was out 2 weeks ago and gave us basically a partial framing. We have a double wall assembly on this project.
Yeah.
So all the mechanicals are in that second wall. So gives us the opportunity to insulate the whole house. And they're just taking advantage of any area that we don't have any mechanical because this has already been blessed. One of the details that you guys had drawn is we basically cast this entire slab in one shot, and we have an elevated slab for the living space, but then a depressed slab for the garage. I've seen other projects where they'll have one slab that is continuous into the basement. For me, I think about water. In the dead of winter, you know, of course you're pitching the slab, but if any water pools, and it can effectively make its way into the living space.
And which is almost inevitable, so you don't want that to happen. So this is a really great detail, just this small step here. Typically for garage slabs, we want a 5-inch slab on grid, and regular residential slabs, we're okay with a 4-inch. There's not much going on there. So this is a 5-inch slab on grid. Looks like it's a great pour. You've cut control joints. Yeah, it's a really great product.
One of the details a lot of people had the question on was actually the way we did our floor system. So it's a little difficult to see in some of these areas, but essentially, you know, these are all non-load bearing. But your floor system, you guys detailed an LVL that essentially is bolted to the inside wall. From an architectural standpoint, that was really driven by these panoramic floor-to-ceiling doors and windows. So we couldn't have that system, that floor system above. But what did that entail in terms of structural design?
That's a good question. Yeah, so a pretty unique detail, because usually we would have some sort of a framing shelf or keep the foundation wall low, you know, sill plate and then a rim board. But here we ran it up high, you know, for architectural reasons. And we have an LVL ledger. Did you use ice and water shields?
We did,
Okay, so we have ice and water shield and the LVL ledger, expansion anchored into the foundation wall. And then we come in with a top flange I-joist hanger and hang it off the LVL ledger. So that's the detail, and it locks everything in place, and you know, it works just as well if we kept the foundation wall low.
Yeah, one of the questions that came up was why didn't we do a shelf? That's a detail that you could do. This is essentially simplifying the concrete work where you're not relying on a shelf detail or kind of having that shelf formed into the foundation wall. You're building a traditional foundation wall, and then the framer is coming in and putting that ledger. So talking to the framers, you know, they said the same thing. Like, we've never done this detail. It's unique. And I had asked, you know, about like, is it more work, or what were their thoughts? He was like, well, it was a lot of drilling and a lot of putting, you know, anchors in. But once they were set, like, it really gave them a nice dead level surface to work up from. We still had a tight tolerance on top of wall because we needed that for our doors and windows. But it does give you the opportunity to allow you to kind of frame from dead zero because you're setting that ledger all the way around.
And it probably saved money on formwork, right? When you poured the foundation wall, right? So it's just a nice rectangular pour.
Exactly. There, you know, all intents and purposes, like, this is a very straightforward L-shaped foundation. The unique parts of it are the wing walls for the retaining wall, and really just the fact that we have this wide opening that is what the garage door, you know, ultimately ends up being.
Absolutely.
Why don't we head upstairs? So basements, you know, primarily living space, obviously some mechanical space. You talked about the steel. You know, down there, really it's just steel columns supporting LVL. You know, you made a comment that there's a lot of steel, there's a lot of structural steel in the concrete, but there's not a lot of steel beams. A lot of this was done with LVL.
Very good point. And LVL and I-joist.
And really intentional layout. But one thing I want to just consider is in the basement, we have all that living space, and where I'm standing here, this is actually outdoor space, but it's above the basement. So
it'll be exposed to the elements, right?
Right, and what we have is essentially a membrane roof here. We have some temporary protection. You just check the stiffness. Is it good?
I do. That's what I always do. That's the check.
But in considering like this being outdoor space and that being indoor space, are you treating the framing differently in terms of sizing? Like, are you considering different live loads inside, outside, or how is that treated? Definitely.
So residential to deck, just in the building code, there's a different live load. The deck live load is 60, residential is 40 typically.
Got it.
But also here, we are also considering snow drifts because this is open, and that snow drift may exceed that 60 pounds per square foot. So we have all those parameters plus the dead loads. And then we kind of elevate the vibration and deflection criteria to make sure that you have a really high performance floor.
Got it. from an architectural standpoint, you see that we're stepped down. In the final condition, we actually end up dead flush from deck to interior. But what you're just seeing is essentially the sub-level prior to us putting our decking, our Ipe decking, and then of course our door system here. Speaking of door system, the doors in here are huge.
Yes.
They're big, they're floor to ceiling, very, very tight tolerances.
Yeah.
I remember being actually on an email chain with you and a handful of other people, and there was a conversation about actually this door and that one, where we couldn't have a deflection of more than eighth of an inch.
Which is pretty tight.
Really tight.
Yeah.
And a lot of that had to do with the way the lift slide door essentially got anchored to what is a quad LVL above, or maybe a triple LVL.
I think a triple and a quad, depending on the condition here.
Sure.
Yeah. So that one's a triple, I believe.
But you came back and said the only way to accomplish that is a flitch beam. What is a flitch beam?
So a flitch beam is, and I know some framers don't like them because they're a pain to put together, but a flitch beam is an
They were okay with putting them together.
Okay, that's good. Yeah. So it's an LVL, steel plate, LVL, then another steel plate and LVL. Sometimes there's 2 plates, 3 plies of LVL. Sometimes there's 1 plate, 2 plies. But generally that's a flitch beam. It's a composite beam of engineered lumber, LVL, and steel plates through bolted together.
Got it.
And with that, you get a super stiff member and strong, stronger than just the traditional, LVL shape. It's just slightly wider.
Yep.
And heavier.
And so on this door, it's over 20 feet wide. That 1/8 inch deflection was super important. And that was really driven because of worst case scenario, back to snow load, live load, the like everything loading up on this house, like in the worst case scenario. And I think someone had explained it as if everything were to basically load this house up at its max capacity and someone goes to open the door, it's gonna be hard.
Exactly, and you don't want that.
Right, but it was, I couldn't help but kind of laugh at that, where it's like, God forbid the door's a little stiff when there's 8 feet of snow on the roof.
Right, exactly.
It's all, for all intent. But that's the consideration that we're making in terms of how to design, and you guys really being agile enough to react to what is being mandated or dictated by the window manufacturer.
Absolutely, yeah. Because if we violate that, and then someone they see we're an engineer of record, and they call us and say, "Oh, I can't open my window during the winter," then that's a bad look for us. Right?
You're not getting that call.
I'm
getting that call.
Yeah, that's true. And then you might call us. So
it's
whatever.
like they're builder. No, let's not call them. Let's call the engineer.
Yeah. Maybe somewhere along the line we'll get the.
Eventually it gets to you.
Yeah, exactly. So
the other part about the flitch beam is that going back to the comment about steel versus wood, is we're also kind of sticking within traditional wood framing.
Yeah.
So being that we have these large openings, talk to me about shear. We're essentially lacking a shear wall. How are you working around that in terms of capturing the shear load or the shear
lateral stability?
Yeah, lateral stability. Thank you.
Yeah. So, one of the first, when we saw the plans for the house, we saw these elevations, and there's huge openings everywhere. Not a lot of solid 2x exterior wall, right? Which that's essentially shear wall for us, because those 2x walls are going to be sheathed with plywood or OSB. And in this house, there's not much. So one of the first things we thought of, okay, we might have to put in some steel moment frames. We talked with you and the architect, and someone raised the possibility of using Simpson Strongwall, which is essentially it's engineered lumber, and they're small segments, and they give you lateral stability in within parameters like this where you don't have a lot of wall. So we explored that, and it seemed to be the perfect product. And I think we've located 5 different.
2 on the outside corner.
Yep. Right.
And then we have two on this opening and 2 on this opening.
Yep. 1, 2, 3. Yeah, that's exactly right. Yep.
Yeah.
So these Simpson strong walls, they are super stiff. They get anchored to the foundation, and it kind of makes up for that lack of solid 2x exterior shear wall around the perimeter.
Yeah.
So it was a great solution, especially on this face of the house. This face, we have a little bit more solid wall, so we don't have any Simpson strong wall over here, and then we also have an interior shear wall right here.
Right.
That makes up for essentially, this opening and that opening.
Yeah, it's funny. A lot of people were like, "Why are you plywooding that wall?" And you just answered that question. It's like, well, it's reacting to the shear load on the home. Like, my role in all of this is always to challenge things, right? Like, how do we accomplish this? How do we not make it overly complicated? And and frankly, I love using steel. I think steel it has its place in a lot of situations. But here, everything was wood and we were just all of a sudden introducing steel.
Yeah.
So that Simpson Strongwall product, came in and we were like, oh, this actually works and we can stick with the wood framing. And essentially have one trade just stay consistent all the way throughout rather than kind of toggling between framer and ironworker.
Yeah, right. And correct me if I'm wrong, but I think you can cut it to the correct height on site, right? So there's a lot of compatibility within the existing floor to floor.
Yeah, and you're using you're using a skill saw and tools that a carpenter is used to.
Yes.
And really just where it differs is that you have these massive anchor bolts that get drilled.
Yeah.
You spec them to be cast in place.
Yep.
And I came back and said I didn't cast them in place. How do I anchor these? There's a lot that goes into setting a foundation.
Yes.
And there's always this conversation around, should I wet set them, or should I drill and epoxy them, or should I use Titan bolts? And
right.
all of that comes into play. Walk me through the reasoning of kind of starting at like, hey, we want you to wet set everything.
Yeah.
And then when I am reaching out asking like, hey, I didn't wet set them, now what?
Yeah. Okay.
Like walk me through like what your thought process is during that.
For traditional like 2x wood framed residential projects, I think foundation contractors are pretty much used to wet setting anchor bolts, right? Mm-hmm. They pour the wall and then they come in, they get their 5/8 inch diameter anchor, space them at 32. Mm-hmm. Goes pretty well. So I would say it's pretty common there. If they want to omit them or if they mess them up, coming in later and post-installing anchors will do the same thing for us, because we're just gonna basically fasten our sill plate to the foundation wall. So I would say it's more of a contractor's preference.
Got it.
Situation. I think it goes quicker if they wet set. That way they don't have to come in later and post-install like all the way around the perimeter. But we have had many projects where they just elect to do it later on.
Yeah.
So I think wet setting is cleaner because then you can get it in and then you can just place the sill plates as soon as the concrete cures. But there's always different parameters, and so we take no exception to post-installing them.
Sure. Yeah. Is there like drilling an epoxy and like a Titan bolt? Are they looked at differently or similar, or is do they each have their place?
So you can do an epoxy anchor, an expansion anchor, a concrete screw. Mm-hmm. Those are all post-installed anchors that would work in this condition.
Yep.
Sometimes it's contractor's preference.
Yeah.
Actually, most times it is.
Yep.
And especially for just for around the perimeter, it's not going to make much of a difference for us. For the Simpson strong walls, those have really high overturning forces, so the tension on that anchor is pretty significant. That's why they ask for such a thick 1 inch diameter, 20 inches long. Yeah, exactly. So post-installing that is a little trickier than if we cast it in place.
Sure.
But we just go in a little further.
Got it.
We look at the parameters, how thick the foundation wall is, how wide the wall is, and all that.
Got it.
Yeah, exactly.
Fair.
Yeah.
So we're standing in the living room. Architecturally, these I-joist, 2x, and LVL, all in the final condition finish exactly the same. Yeah. They get all wrapped in an oak beam. So this was, hypercritical in the architectural design to make sure that these laid out perfectly on center. But when you're looking at it right now, it looks like they're all different materials, all different sizes, and so on and so forth. Why do we have I-joist, LVL, and 2x dimensional lumber? What was the reasoning behind that? Architecturally, I know that where the 2x lumber is, that's where we have a stone floor above. Essentially, that is recessed down about 2 inches. So when we go to install our hardwood, we can then build up our stone floor to be completely flush. But why swap that material to a 2x dimensional lumber versus using an I-joist?
So here, like this span, I think it's 20-something feet.
21,
yeah. 21 feet. So a 2x is not going to, achieve that span. So, that's why you see an I-joist typically spanning from exterior wall to exterior wall, which is pretty clean.
27 feet. Sorry.
27 feet.
I believe it's 27.
Wait. Oh, it's something like that, yeah. So these are 16 inch. So it's a really long span. Yeah. So the only way we can span from exterior wall to exterior wall is an I-joist, and these are 16 inch I-joists.
Yeah.
We also have a pretty unique spacing here. I think kind of related to what the architect wants, right? In terms of that exposed ceiling.
Yep.
It's 1 foot 1 3/4, which I'm sure your framers were like, why are we doing this? And now they know.
They knew.
Yeah,
It was like when they showed up day one, I was like, hey, first floor ceilings in the living room and kitchen, those joists need to be exactly what they say they were. And they were great. Like they built story poles and made sure everything landed where it needed to land.
It's pretty cool. So it's going to be exposed structure somewhat, right? We're going to see the bottom flange of these I-joists, which are, those are 2x4s on the side there.
Yep.
So that's why we have the I-joist spanning the exterior wall. And
Sure.
then here, like you said, I think these are recess, the bathrooms above us.
Yep.
So we dropped the framing 2 inches or so with the 2x's there and there. So that's, again, just to accommodate that, what is it, a thin set mortar and
Thin set
tile.
mortar and stone, yeah.
Stone, yeah, exactly. And we doubled up the 2x's
Yep.
because, again, we want that pretty stiff.
Right.
And then LVL framing around it where we drop that framing. So that's why you see the 2-ply LVLs here.
We could have used I-joist, but there was really no benefit.
Right.
You said, hey, double up a 2x and we've got our capacity.
Exactly,
Yeah.
right. Frame around it locally, exactly, yeah.
Yeah, and that's like, for me, that's the balance of, what we're using in terms of material and making sure that we're not overcomplicating just the understanding of it.
Yeah.
Where it's like that decision ultimately was from a cost perspective, where it's like, well, we don't need to buy an I-joist, a 2x10 works.
Yeah.
So 2x10 is going to be less expensive. And then it's just a matter of making sure that the framer understands, hey, these are I-joists, that's an LVL, that's a 2x10.
Yes.
And when you're looking at it, when you look up right now, it looks more complicated than what ends up being the final product here.
Yeah, definitely, right. Yeah.
Speaking of this area, we also have quite a bit of plumbing that is penetrating, quite a bit of structure.
Yeah.
So, some of these are pretty typical. But this one, for example, this is a big LVL here, and this is one of the first questions I approached you with. I said, hey, I got this 3-inch line. I literally have nowhere to get it down from this living room. Soffits and padding walls out don't exist.
Yeah.
It completely ruins architectural details.
Right.
Ben, the only way I can get this 3-inch down is going through that LVL. How do I do that?
Yeah.
So you were quick to respond, hey, this is how you do it. This is what I want you to do.
Yep.
Walk us through what we got going on here.
Okay, so yeah, this is slightly bigger penetration than what we have elsewhere, right? So this beam here also has a post landing on it, so there's a little bit more load on this beam.
Mm-hmm.
So kind of look at where the penetration is relative to the exterior wall and where the post comes down. I believe the post is maybe somewhere around here, or maybe somewhere maybe closer to here. So looking at that, we didn't want the penetration too close to the exterior wall. Because shear starts to govern at the end of the beam.
Got it.
We didn't want it too close to the post, so we located it more or less in between the post and the exterior wall. Mm-hmm. And we found that this part of the beam would need to be stiffened up ever so slightly. So the way to do that would be to take 3/4 inch plywood, which looks like it's installed, and glue it and nail it to the beam on either side prior to doing the penetration. Looks like that's exactly what you guys did. So the plywood's in place, and then you came in and drilled right through it.
And
penetrations.
What that is essentially doing is just adding additional stiffness to that beam, going from a 3-ply LVL to essentially a 3-ply with plywood.
Exactly.
Kind of going back, a little different, but like similar to like this whole flitch beam where you're adding additional material to stiffen that section.
Right, exactly, yeah. It's a very small percentage of increasing the stiffness, but it's what we needed at this location.
Got it.
Exactly.
And then in terms of, so this one here, we had no option but to notch the bottom of this 2x10.
Yep.
And because we can't, if you look closely, there's bottom of pipe can't be any lower than that because that's our finished ceiling height. So I had reached out, I said, hey, there's nothing I can do here.
Right.
Walk me through like the thought process of notching the bottom of that 2x.
Okay, yeah, so this is a spot where maybe, I could get in trouble if I say something about the code, but I'll just say it anyway. So the code says you can notch a joist up to 1/6 of its depth in the middle third, right? Without even looking at it.
And that's International Builders Code.
Yeah, the IBC, yep, exactly, yeah, which is referred to by the Massachusetts Building Code.
Yep.
So here, I think you're slightly above that 1/6, but you told me that dimension from top of joist to top of notch. Mm-hmm. So then I just ignored that bottom section of joist elsewhere and just ran it as, a 2x true 8-inch or whatever it was. And that works by itself. So with that, we said, okay, we can omit that bottom section. We know it's fine.
Essentially looking at it as like a smaller member.
Smaller member, yeah.
Got it.
Yeah.
And that works, yeah.
Yes, exactly.
And that's probably largely due to the fact that it's a short span.
It's a short span because we're framing around for the bathroom above.
Got it.
Yeah.
Anything else in this space that you're looking at? And we have, all of, essentially we have a perimeter LVL around the whole house. You can actually see a lot of the anchor bolts for these flitch beams. Everything is hung off the side of these LVLs. Very little actually sits on top. It's really this kind of LVL band around the whole home.
Framing into the face of it. Yeah, exactly.
Is there anything like that you're looking around and seeing? If it's wrong, feel free to point it out.
No, yeah, everything's looking good. I mean, I see all the hangers in place. That's the first thing I usually check for.
Okay.
We had a bit of a post installed situation over here with an angle.
Oh yeah.
Is that in place?
It is.
Yeah.
So this was actually a product of, you guys had designed it. We have this quad LVL that was a triple.
Yes.
Switched to a quad, I forget why.
To relieve some of the depth, maybe to push it up a little bit.
I think you're right. And we had ordered a quad, you essentially had spec'd a quad LVL hanger. We showed up and we realized that, well, there's nothing that you can hang it to on the outside, so then we needed to get a concealed flange. And the only concealed flange was very small.
Yes.
And we put it in there and we all kind of laughed at each other and said, this is literally not holding
especially
a quad LVL.
Considering the loads above, right?
Right.
So,
we have a steel HSS rafter up there. There's a lot. So we have this false ceiling here, and I said, hey, we have space to add something. And you had spec'd a 6x6, I think 3/8 or ½ inch thick angle, and we bolted it up into the LVL and then bolted it back into our post here.
Exactly. Yeah, that's right. And there it is there. Yeah. So it looks like the this vertical is hidden by the 2x there, but
That's
you already
correct.
sent photos of that.
Yeah.
I think. Yeah. So.
I did. For the record, I did send photos. If I didn't, I have them.
Right. Yeah, so that's the angle. So we had a really light hanger, just didn't have the capacity, and it was off by a bit. So we had to kind of come in with a solution that really kind of worked with the as-built conditions, and obviously pretty tricky. So lagging an angle up into the LVL and then lagging into the post with a longer vertical leg, that did it for us. So yeah.
I think what's important to point out about something like this is a product of, everyone's moving and trying to do the best that they can and try to capture all the details. We all miss stuff.
Right.
And there's kind of two schools of thought here. I could have put that concealed hanger in and left it.
Yes, right.
And 50 years, 60, could have never been a problem.
Yeah.
But the problem is by me just moving forward quite well knowing that, hey, that doesn't look like it's the right thing.
Yeah.
I'm putting everyone at risk. And instead, it's like, I can hop on a call with you and say, hey, this is the condition, shoot you a text, this is what we got going on.
Yeah.
Of course, we follow up with a confirming RFI,
right.
to document it. But ideally, having a good relationship is a product of where we end up. Because I'm able to ask the question, you're able to look at it and be like, yes, that is wrong, we should fix it, here's a possible solution, or give me an hour and I'll get you a sketch and I'll send it back to you.
Yes. We know a project like this, you want to keep your framer moving, right?
Yeah.
We really appreciate how you reach out pretty quickly and you almost propose a solution sometimes, which makes it a lot easier for us. Given the parameters, you're on site, we're not all the time.
Yeah.
So when you kind of come to us with a solution that's almost there, we just need to bless it or tweak it. And then, we give you the answer and then you come in later with an RFI for record, that's doing everything that we need.
Yeah.
Right.
That's
checking all the boxes there.
Honestly, anyone that's watching this, that is the way this is supposed to work. And I'm not trying to give myself a pat on the back, but approach a problem with a solution. Yeah. And I could propose a solution that's wrong or way off base. But the fact of the matter is you have a pretty high likelihood of understanding the problem and proposing something that's almost there. Like you said, it's hey, it's almost there, I just need to go through and bless it.
Exactly.
Talk to me about this, my favorite space. The 3-story flared 9-foot by 9-foot skylight.
It's a pretty wild condition here.
So what is going on structurally in this space? We got LVLs, we have steel, and of course we have this, as you look up, there's just LVL upon LVL to basically frame this opening for what is a single piece of glass.
Yeah, exactly. Right. So we have this big skylight, and in the central section, you have this kind of recessed, flat portion of roof, right? And then on either side, you have basically a hip roof. Mm-hmm. The hip continues that way, and then this way. You see central LVL lines underneath that hipped section where the rafter, where the sloped meets the flat part. We frame around the skylight. There's a lot of framing going on here, a lot of posts down. You see the big shear wall. You have a massive steel beam behind us, one of the only steel beams, in the floor framing.
Yeah.
There's a really interesting detail with this wall being slightly offset where the steel fabricator welded some stiffener plates to catch that post and Looks like it came out fantastic.
Yeah.
Great coordination on their part. This is a pretty big space. I'm sure the architect's pretty happy with how this turned out. Like, this is pretty cool.
Yeah.
Yeah.
I think it's worth pointing out, like, people are gonna be like, well, why is that wall offset? And that's an architectural detail, basically what Vincent's trying to accomplish with the doors here on this essentially banquette that folds open. So when everything is closed, you have this flush condition. And again, this is an exact product of thinking all the way through what the intent is and working backwards. Yeah, exactly. Where it's like, okay, well, offsetting that beam and adding a couple stiffeners, it's like, in the grand scheme of things, isn't overly complicated, but you'd never be able to accomplish that detail if you didn't think from the very end and backwards.
Yeah, definitely. Yeah. And some people might say, why can't you just push the steel beam this way a little bit? Right. And then the answer is that with the openings here and there, you push the steel beam this way, it's now running into the edge of this opening. So now this beam wants to be a steel beam. Right. Or a heavier flitch beam, and same thing there. So we were able to keep it pushed over there and just catch the post with that stiffener plate. So it's kind of a money saver in the end to be able to do that.
Yeah, it's hard to, it's sometimes hard to quantify that too, where it's now we're just adding steel. It's like, yeah, but we added one steel versus if that was 2 inches forward, you'd have 2 pieces of steel. And then it's like, well, then how are you posting the steel down? And
exactly, trickle down effect.
Right. And that's, a product of a good team and making sure that we're all kind of working through the same the same intent. Right. Anything you want to look at over here, or should we go upstairs?
Why don't we go upstairs? I want to see those bent frames.
Yeah. Yeah, so the staircase, this one here is actually temporary, which is why it bounces as we walk up it. But that is that architectural staircase that you guys worked through from a structure design around it, and it'll be treated by itself. I love this view because you still have a ton of height, and it's unfortunate all this gets wrapped up, kind of. But you can really see how you have this continuous LVL down to the post to those stiffeners, and then you have your tripled up hip rafters and on each corner there. Triple LVL, and it just, like you said, there's a lot going on.
Yeah, it's really gorgeous. Your framers did a great job. They should leave it exposed.
I know. They really did a fantastic job. So in the primary, we have these huge, ceilings. In the shower here is over 12 feet tall, 12 feet in the bathroom. But the steel that we're talking about is actually up here. And this is it considered bent, or?
Some people call it a rigid frame or a tube steel bent frame.
Okay.
It's bent because it has at the elbow there.
Yeah.
It's it's a full pen weld, so it's continuous. And same thing over there.
For those that are watching, we're not taking a 6x12 tube and bending it. We are fabricating it, but it's considered with that full pen.
Yes, exactly.
Weld, you're considering it as like a monolithic piece.
Exactly. We consider it a continuous piece. Yeah,
right.
That's right. Yep.
So these here, so there's one here, and then there's 2 over on the smaller hip roof section. But this one, walk me through what it's doing.
It's picking up a lot of this roof here. And you notice that it's right at the transition from sloped to flat roof to sloping this way. So it's the hip end of this roof. And if you notice how the ceiling is kind of recessed up, it's mostly, I'd say it's partially vaulted. With this vaulted space, you can't have a low beam at the ceiling to pick up the transition from LVL, hip beam, and all these rafters. Normally we would just drop a post down and collect it with a beam.
Yeah, so capturing that wall on the flat roof and then transferring it into the 2 exterior walls.
Yeah, that's what we want to do. Right. Exactly, yeah. But when we don't have a flat ceiling, everything gets pushed up. There's really nothing we can do with wood at this condition. Mm-hmm. So
then you end up having a hinge.
Yeah, exactly, which you can't do with wood.
Right.
That's why we now have a tube steel bent frame, which is sized to collect those point loads. There's one there, there's one there. You have the roof framing at this end coming into it. Yeah. So this tube steel frame is sized to collect all those loads and then distribute it to the exterior wall.
And well, let's talk about the exterior wall because I'm landing on 2 giant openings.
Yeah, right.
So how are we taking a tube steel and landing it on top of a window that's almost 10 feet wide?
You have an LVL size for that load. Right. Again, size for pretty stringent deflection criteria.
Quad 12-inch LVL sitting above that window.
Exactly. And then the end of the tube steel, which you may be able to see, if you zoom in, is an angle lagged into that LVL.
Yep.
Yeah, so that's restraining the end of that tube steel, which is essentially a vertical reaction.
And that's essentially holding the wall from moving in and out as well as holding the steel down.
Yes, exactly. Yeah, the tube steel itself is stiff enough to resist any outward thrust.
Sure.
Yeah.
I'll give credit where credit's due. RMS did a great job fabricating these. He also, if you look on this side, it's actually quite unfortunate because if you look up, he actually hand painted these in his shop, and it says with the white oak logo as well as 45 white oak. Yeah. And then on the drop, it said RMS Iron, and on the other drop it said NS Builders. And they were on site and immediately put in and immediately sandwiched with wood.
Yeah.
And I was like, I wish we had more opportunity to capture that for you. Right. But it's a product of him believing in what we're building here, which I think is a huge part. Everyone understands what we're after with this project, and it's super exciting to have people that are involved at that level. Yeah. What about the double wall assembly? From a structural perspective, was there any consideration, or like, was this really just, hey, you guys can do what you want? All of our structure is in this 2x6 wall. Yes. And then we built these, and this is a product, we'll dig into it in a future episode with Vincent, but in short, these walls are installed because of, having a chase way for mechanicals, but also to kind of fine tune square footage for what we were allowed to build on this lot. And all the detailing for how our interior finish interacts with our windows, including all the recessed shade pockets and things like that. Right. But is there, from a structural perspective, is there anything that you're considering in terms of doing that double wall?
We're not really relying on this wall, right? It's a non-load bearing wall. Mm-hmm. All our structures coming in the 2x6 exterior wall. Yep. So we just make sure that our framing is sized to, support an additional wall on the inside, which it is. Yep. It's not much considered, everything else. So it's a really good solution architecturally and for MEP and all that, but for us, we don't really care. We don't really need to know about it. Yeah, exactly. Yeah, right. Yeah.
Why don't we go look at the other tube steel? But before we do, this is, just to kind of put a bow on it, but this is this is those two areas that you have the dimensional lumber below, which is recessed. And you can see we have finished floor +3, finished floor +3/4. So that tells me that this is 2¼ inches lower than that. Yep. Because ultimately, when we're standing in the shower, we're gonna have this flush threshold between our blue marble and our hardwood that flows throughout the rest of the space.
And this over here, Nick, what's the
same here? We're actually going to take the blue marble and put it underneath our vanity, and so we have this kind of almost as though it's kind of like an area rug under a piece of furniture. Yep. But it's blue marble under a vanity.
Right. Okay.
So you'll see that every bathroom is prepped that way.
Yes.
We have all our secondary bedrooms and bathrooms in here, but then we get into this smaller hip section. So we have these tripled up hip beams. Here's another area that I missed. And we talked about, but essentially we have our steel bent rafters here, and we have 1, 2 that support essentially where the hip and the ridge meet. But there was this note, I think it was on your drawing, but it basically said the steel guy can either weld a flange or the framer can install a hanger. What happened was the framer assumed the steel guy was doing it, and the steel guy assumed the framer was doing it. So ultimately, you came back and I said, hey, what if we support it below? And you had said, yeah, let's add some angle iron. Walk me through that, because we do have steel. We have a ridge between them, so that steel can't basically overturn. Exactly. And then you have these hip rafters that are anchored on the corner and then lean against the steel. So in theory, like, they can't go anywhere. What is the purpose of having that clip below the hip rafter? Basically,
if you strip what we're looking at of all architectural elements right now, you'd have like an LVL ridge beam, and we just look at one frame, LVL ridge beam, you have 2 hip LVL beams coming into that bend frame, essentially putting a reaction onto the ridge point of that bend frame. That reaction does need to get transferred into the tube steel frame. Sure, there are some funny things happening with the architectural elements. You have some collar ties, everything's kind of tied together, but again, when we design, we don't really account for that. Yeah. So this is also a very common thing. It's like 2 trades interacting with each other, the steel fabricator and the framer. It's something that does get missed because, it's kind of a fingers pointing at each other situation.
Right.
In the end, we do need to have some sort of positive connection between LVL in tube steel, and I think we came up with a pretty good solution in the end.
I think that's an interesting point. Like you think about how all of these architectural elements are in fact helping the situation, but you know, you're essentially thinking in a way that if someone decided to renovate this later and cut all the collar ties out, like the roof doesn't fail.
They could do that, exactly.
Right. And,
yeah, they could vault it entirely if they wanted to.
Right, and that's where it's like you're designing kind of what is required with the complete, you know, by completely ignoring architecturally what you know, we end up with, because that architectural detail can change.
Right, exactly, yeah. And going back to what we discussed over there, if this was a flat ceiling, we probably would, you know, find a solution that did not involve tube steel bend frames. Right, but with this vaulted ceiling, partially vaulted, there's some restrictions there.
And that was actually a product of what we were allowed to build here in Wellesley. You know, they essentially were looking at attic spaces, additional square footage, despite the structure that would never allow you to be up there, you know, just the way it calced, and you know, and this was a product of that. We ended up vaulting all the ceilings in the second floor bedrooms to counteract that, which ultimately, architecturally, we end up with a really nice, cool detail, really great ceiling heights in these rooms. To your side, it's like it does make the structure a little bit more complicated and requires us to have more steel than wood. Right,
exactly, that's spot on, Yeah, and if I remember correctly, that was something that came back from the town a little bit later down, you know, the design process, right? So we kind of had to make some decisions.
Yeah. It was kind of, I won't say fire Joe, but it was definitely like, hey Nick, you're gonna have to create, you know, these more expensive ceilings, and there was some pushback from my side. I was like, this, like, why? And ultimately, you know, it's the way they judge the home's size. And there's a lot of, you know, there's a lot of benefit to that in terms of controlling homes from being built too large. And it doesn't always work in our favor, but I think ultimately we ended up with a much more pleasing product in the end.
Yeah, absolutely. So. Yeah, came out great.
Ben, how do we look?
Looks good.
Looks good?
Yeah. Wait, hurricane clips are in place?
You can't see them.
Can't see them. That's the thing that we look for on the roof. I see one right there.
There you go.
Yeah.
It's funny when this wall gets in your way a lot. So you can't see.
Yeah, the double wall. Yep. Yeah, looks fantastic.
Awesome.
Let's see these big spans over here. These long hip members. Yeah. It's pretty cool. So this is the low part of the roof right here, right?
Yes.
Yeah.
So we essentially, the two hip roofs kind of come together here, and in its final condition, we'll have essentially a continuous gutter. That will capture all the water in both directions and get it out to 2 downspouts. But traditionally, you would avoid that in more traditional looking homes. But this is anything but traditional.
No, definitely not. Yeah.
But yeah, I remember seeing this hip beam go in, and you can see like the hanger details, and it just, you know, super complicated in the way everything kind of intersects.
Yeah, absolutely, yeah. It's kind of deceiving. It's actually quite deep. That's an 18-inch deep beam, but the insulation makes it look like, you know, it's just popping out of the ceiling just so slightly, but that's not the case. It's a sizable beam.
Yeah, I mean, Koopman was great. They supplied all the lumber on the project, but every truck would show up, and I'm like, man, that's a lot of LVL.
Right.
And then right behind it would be another one, and it's, you know, it's interesting to think about what we're able to accomplish architecturally and for your sake structurally with engineered lumber like LVL.
Yeah, absolutely.
You know, we're able to accomplish a lot of really intricate and cool detailing that we otherwise, you know, it would have been very challenging to do with lumber.
Absolutely. Yeah, definitely.
Awesome. Yeah. Well, Ben, I appreciate you coming out, man. I appreciate you checking on things. I'm glad you were able to come out before we close the walls up.
Yeah, I know. That's always the goal, right? I know, depending on schedule, sometimes it can be a little tricky to get out here, right?
Totally.
Yeah.
And yeah, we'll you know, if there's anything that you want to add to our punch list, we'll take care of it. But guys, I appreciate you sticking around. Another structural walkthrough of our 45 White Oak project. Stick around for another episode in the future as we roll into closing these walls up and getting into the finishes of what we got going on here.